going on in China on ocean negative carbon emissions, the ONCE program, ONCE. And we're really delighted to have a delegation from China and a number of partners working with China on a really what looks like a very comprehensive program of research and development around ocean carbon removal. And you know, we've all been toiling in this space for a while, but we don't have perfect communication. We don't necessarily know what each other is always doing. Events like this are an opportunity to share some of that knowledge. And so again, I'm just really delighted to have our Chinese colleagues here. They have a pretty robust lineup of work. We are exploring additional collaboration, and we hope that this will be the first step in bringing our two programs closer together and engaging Ocean Visions and its network with ONCE. So with that, I'm going to invite Ming Zhao to come to the stage and lead what is going to be, I think, a very interesting session.
So good morning, everyone, and welcome to this special session. And first, I would like to express my greatest gratitude to all of you for coming to this session. I would also like to thank the host, Ocean Visions, and the AGO team for arranging this special event. In the last 2 days, we have heard a lot of CDR, the carbon dioxide removal. The Ocean Negative Carbon Emissions, the short name ONCE, is a special international program and for finding solutions for carbon dioxide removal. ONCE technology will involve reducing carbon emissions from human activity such as shipping and fishing, and active carbon barriers in the oceans through various technologies. ONCE is now one of the United Nations Decade of Ocean Science programs. This initiative aims to strengthen international collaborations and investments in ocean science to support sustainable development and better understanding in the ocean, to support sustainable development and better understanding of the ocean role in regulating our planet climate. Today we'll have 3 sessions. The first, we'll have 2 co-chairs give the opening remarks and introduction. And second session will be on ONCE technologies, and the third session will be a discussion on how to enhance the collaboration between global ONCE and potential partners. So now it is my pleasure to introduce you the co-chair of Global ONCE. So Carol Robinson is from University of East Anglia to give the opening remark. So I need to, because it's the Easter holiday time, so she will not be here. So I need to play the video, but seems like the screen is different from what I saw in the morning. I don't know how to advance to the next one. So let me see, maybe I can figure out. Okay, here we go. All right.
Hello everyone, and welcome to this session on ocean negative carbon emissions, a regional and global effort towards carbon neutrality. My name is Carol Robinson, and I'm a marine biogeochemist from the University of East Anglia in the UK, and together with Nancy Zhao from the University of Xiamen in China, I'm a co-chair of the UN Decade Programme, Global ONCE. The lead partners of Global ONCE are PICES, the North Pacific Marine Science Organization, ICES, the International Council for the Exploration of the Sea, the SCORE Future Earth Global Research Networks, IMBA, Integrated Marine Biosphere Research, and SOLAS, Surface Ocean Lower Atmosphere Study, and the World Climate Research Programme, WCRP. Global ONCE was formally approved at the UN Ocean Conference in June 2022. The aim of Global ONCE is to provide data, knowledge, and best practices to enable society to develop safe mitigation and adaptation approaches to climate impacts. And as any other UN Decade programme, it embraces many individuals, projects and programmes, some of which you can see here. The programme has a secretariat at the University of Xiamen, and this, together with some of the fundamental science, marine infrastructure and networking and educational activities within Global Once, are underpinned by a regional research project funded by the Chinese Ministry of Science and Technology. The aim of Global Once is broken down into 4 objectives or outcomes. The first, to develop an international network of field stations and research facilities available for co-designed interdisciplinary research. The second, to develop an evaluation framework for mitigation and adaptation approaches. The third, to coordinate technical and personnel capacity development and ocean literacy. And the fourth, to facilitate equitable policy, governance and societal understanding. As you can see, these objectives intersect with those of several national and regional networks working on ocean-based technologies for the safe and effective removal and sequestration of atmospheric carbon dioxide, including those of the Ocean Visions UN Decade Collaborative Centre for Ocean Climate Solutions. At the moment, the activities of Global Once include confirming the terms of reference and membership of the International Advisory Committee, co-chaired by Jean-Pierre Gattuso and Sarah Cooley, and the Scientific Steering Committee, co-chaired by Nancy Zhao and myself. Appointing personnel, co-developing an implementation plan and communication strategy, and convening workshops and panel discussions, including one at the UN Ocean Conference in June last year, and another at the World Ocean Week, convened in Xiamen in November last year. Which brings us to the meeting today. As you can see from the programme, the session starts with an overview presentation by Nancy on the science and technologies to be developed within Once, followed by 3 focused talks on the technologies to be deployed and 3 on the required underpinning research on the biological and microbial carbon pumps. The talks are followed by a panel and audience discussion on potential collaborative activities to take forward our collective aim to devise safe carbon dioxide removal technologies in order to reach negative carbon emissions. I'm really sorry that I can't be with you in Atlanta today, but wish you a very successful and productive session. Thank you very much.
Okay. So as Professor Robinson introduced, it is about the willingness to do things differently in response to climate change and the need for carbon neutrality. We need leaderships and role models. So next speaker is the chair of Global Once, Professor Nianzhi Jiao from Xiamen University. And he will share with us the overview of the Global Once. And unfortunately, he won't get the visa in time, so he will, we will present as a video too. So let me click the button. All right.
Hello everyone, welcome to our session. My name is Nianzhi Jiao. My topic here is about the UN International Program, Global One. Once here stands for Ocean Negative Carbon Emission. As we know, climate change is the biggest environmental issue we are facing today. And the major cause for global warming is anthropogenic CO2 emission. So that's why we have to do negative carbon emission. And the ocean is the biggest carbon reservoir on the Earth, played a very significant role in regulating climate change in the history of Earth. But now, because it already absorbed about 93% of the total CO2 on the Earth, it's a kind of at a critical point. So we have to be very careful. So that's why we initiated an international program for ocean negative emissions. And in addition to the UN International Program, we also have a program on Once supported by the Ministry of Science and Technology of China, where we have 5 missions. Number 1, innovative research. Number 2, construction of a research platform. 3, demonstration of the ONE's approaches. I mean, the approaches for ocean negative carbon emissions. And number 4 and 5 is about international communications and science popularization. So to do effective negative carbon emission, we have to understand the mechanism of carbon sequestration in the ocean first. And the known mechanisms, including solubility pump and the carbonate counter pump, or CCP in short, as well as the biological carbon pump, or BCP in short. Because the SP, the solubility pump, is not really under control. I mean, you cannot really manipulate, so just leave it. And for the case of the CCP, we have to focus on the counter process. I mean, when you have one more of a precipitation of carbonate, you're going to release the same equivalent amount of CO2 theoretically. And the mission for us is to try to reduce the CO2 emission while you have as much as possible carbonates down there buried in the sediment. And for the case of a BCP, because of the flux down there to the sediment is very little. It's only about 1% or even 0.1% of the total carbon fixed in the surface. So then where is the rest of organic carbon gone? Scientists did know there is a huge dissolved organic carbon in the water column for a long time, but we did not know how it was formed. About 10 years ago, we proposed a new concept, new mechanism called microbial carbon pump, referred to the microbial physiological and ecological process that transform organic carbon from labile states to refractory states. So being refractory, it resists to further decomposition and utilization, and then it can stay in the water column for a long time. Actually, the resident time of the RDUC in the current ocean is about 5,000 years. So now for these projects, I mean the advanced projects, we have to understand the interactions of these mechanisms. I mean, the interactions between MCP and BCP and CCP. Our hypothesis is that there could be a kind of synergistic effects of all of these pumps. And if you understand the process and the mechanism behind, you can control the boundary condition, you could reach maximum output of the carbon sequestered in the sediment, reproduce what happened in the history of the Earth. I mean, the carbon sequestration in forms of organic and inorganic, and the outputs of this total carbon would be the maximum. So that's the hypothesis. And we do have some geological records for evidence like this. You can see the rocks, the sediments, the carbonates actually were induced by the microbial processes. And you can also see the microbial processes for carbon sequestration in terms of organic carbon and inorganic carbon under the microscopy. You can see the pictures like this. So they have mechanisms for carbonate precipitation inside the cells and outside the cells. So this is a case, the example of for innovative research. And by understanding the mechanisms and the interactions between organic, inorganic, and living, the non-living, biotic and abiotic processes, you could reach, you could turn the CCP from a counter pump to a positive one, and you can enhance the BCP, and you can reach maximum output of the carbon for substitution. Okay, for our research platforms, we're gonna build some facilities like this. This infrastructure is called Marine Environmental Timber Systems, or MAES in short. As you can see, they are in a series, so providing you with the conditions for gradient study to simulate what had happened in the history of Earth for scenario study. And you can acquire process parameters for modeling, then enable you to enact the past and predict the future. And this one is a mini-max already set, already built there out there in China. And we also have intelligent simulation system like this one. You can see there's two cells, one on the bank, another part in the water. And this is can be called a digital twin, which is a very popular. We could have even bigger ones like this, which is called Oceanic Residence Research Platform. As you can see, there are hotels on it, and you can stay there for a long time for in-depth study. And more commonly, we have the marine ranching facilities like this. Actually, there are already more than 200 cities out there along the Chinese coast. These are basically designed for marine aquaculture purpose, but they're also good for wines for ocean negative carbon emission studies. Okay, for on-site demonstration, I would like to show you three cases. One is land-ocean integrated eco-engineering. Second one is artificial upwelling application to the seaweed aquaculture area. And the third is ocean salinity enhancement via wastewater treatment. For the first case, as you may know, there is a paradox that productive coastal waters are often sources rather than sinks of atmospheric CO2. How come that case? It's actually just because of the perturbation by human activity, human anthropogenic impacts like eutrophication. Under repeated nutrient condition, bacterial cells could be very actively inspire organic carbon into CO2. And if you reduce the nutrients, then the cells can store organic carbon inside the cell, like this, the white dots. So that's why we propose the idea that to increase carbon sink in the coastal water by reduce fertilization of the land, because in many cases, the farming area is over-fertilized. The second example is the seaweed culture-based comprehensive wines approach, which could be a good paradigm, where you can apply clean energy-driven artificial upwelling to bring up the deep water with the high nutrients to the surface to support carbon fixation by the seaweeds and the phytoplankton as well in the aquatic zone. And this process can also release the bomb of eutrophication in the bottom of the sea to mitigate hypoxia and water acidification down there. And once the algal bloom is formed, you could kill the cells with the hydroxyl radical, for example, to break the DNA and keep the cells intact. Then you apply clay to drag down them down to the bottom of a barrel for a long time substitution. Furthermore, you could apply alkaline minerals to enhance alkalinity, and then you could turn the carbonaceous counterpart to be a positive one. So this way, you could promote BCP, CCP, and MCP together to achieve maximum outputs of carbon sequestration in the comprehensive form, including inorganic and organic, living and non-living forms. Finally, it is in accordance with the landing protocol. So the seaweed culture based comprehensive WANS approach is reasonable, feasible, and legal. And the third demonstration would be ocean alkalinity enhancement through the wastewater treatment. I think Dr. Wei Jun Cai is going to talk about this, and I will skip it here. And after we do the experimental study, we do some practice in the field, we can produce some protocols for the techniques to develop international standards, which people can follow, and then to do practice in other places around the world. For international communication and science popularization, we have a working group on the ICES and the PICES. ICES refer to the International Committee for Exploration of the Sea, and the PICES is the North Pacific Marine Science Organization. This working group has been there for nearly 3 years. And we do have connections with the international partners and the relevant international organizations. And our collaborators from all over the world, there are already 78 teams from 33 countries joining us. And it is still open to interested individuals and labs and teams. And we are now setting up some focal points around the world for scientific communication and science education. And we did have some international activities like this, which is a side event to the UN Ocean Conference last June. And we have a virtual lab for science education. And we did open a class on the website, and which is called Habitable Earth. You're welcome to visit it. It's now in Chinese and in English. And this is the headquarters in Xiamen. And here is our website for Global WANS. You can visit it for more information. Okay, so before I finish up, I would like to give my sincere thanks to all the partners and our participants and the international organizations supporting ours. Okay, thank you for your attention, and you're welcome to join us. Thanks.
Okay, both Professors Carl Robinson and Nian Zhijiao gave an overview of the WANS program, and it is indeed a program intended to find various solutions for various climate change problems. So next we have a few talks. So the first talk was given by Professor Wei Jun Cai from the University of Delaware, who is working on alkalinity experiments. Please, Professor Cai. It's preloaded already, so it's coming up. So let me see. We need to move a couple of slides back. Here we go. Here you are.
All right. Thank you. It's such a pleasure to be here, and I want to thank Nian Zhijiao and the committee for inviting me to talk about. The short title is Alkalinity Experiment. The full title really is Coastal Ocean Alkalinity Enhancement as a Means for Achieving Ocean Negative Carbon Emission. And again, I'm Wei Jun Cai from University of Delaware. Actually, I was a professor here in the University of Georgia for 19 years, so it's great to be home. Since Nian already set up a stage, so I'm not going to talk about the needs for CO2 removal in the atmosphere, and this audience know that we need to mitigate the CO2 and global warming. So I want to talk about why we the ocean. First, the ocean contains 50 times of the carbon dioxide compared with atmospheric CO2. So really, through the geological history of the ocean atmospheric system, it is the ocean that the much larger reservoir that controls atmospheric CO2. And second is ocean has this vast area, surface area can interact with the atmosphere, so you can do the job a lot easier rather than compare with some other approach like direct removal CO2 from atmosphere. But the key is we still need to remove CO2 from the atmosphere, right? So and then the ocean DIC has a long residence time. So if you can lock CO2 in the DIC pool, you don't need to worry about it release back to atmosphere right away. And finally, ocean is currently acidified, can use some help. So there is a co-benefit for ocean acidification relief. So how do we achieve this? As I mentioned that we have to remove, the final goal is to remove CO2 from atmosphere, right? But the way to do that, to use ocean alkalinity enhancement is to increase acid CO2 gradient, so to bring down the CO2 in the ocean, surface ocean. So we can do several ways. The first is you can neutralize the CO2 by carbonate and into bicarbonate. And that is what we already, the natural process, quote unquote natural, is when ocean is acidified, currently CO2 is being removed, neutralized by carbonate. But we can accelerate that process by, for example, adding limestone carbonate, right? Unfortunately, ocean is already, surface ocean is supersaturated with carbonate, so that's not going to happen in the conventional way. And second is we can add hydroxide, and that can be done by adding sodium hydroxide or calcium or magnesium hydroxide, or equivalently by apply silicated minerals. That's actually because it doesn't contain carbon, so it actually is in a sense providing OH to the system. So I want next to say a little bit how effective of adding alkaline minerals to the ocean. So this figure shows with DIC and alkalinity, you can consider this. This is the total amount of CO2. This is a base in the ocean, right? This figure shows with the color bar is the pH, 9 and 6 between, so high pH and low pH in the ocean. And I also put 2 lines here. Aragonite saturation state equals 1, 5, and 10 here. And these lines are PCO2, 100, 200, 300. So then if you put a line of current atmospheric CO2 of 420 ppm or micro atmosphere. So this line shows if you start with this ocean current condition by adding calcium carbonate, you increase DIC and alkalinity in a 1:2 ratio. So you bring it from high CO2, sea surface 420 towards low CO2 this way along this line. And then this will, ocean surface will take up CO2 by increased surface CO2 as a result. And you can add OH, that basically you don't add any CO2, but you increase alkalinity, so that through this process. And that's more effective because you can rapidly decrease PCO2 from 420 towards, by adding only a little bit of OH, you can reduce surface PCO2 greatly. And then ocean will take up a CO2. There's another way that will both remove CO2 and, to increase alkalinity. So you could doing like cement. It has surface of carbonation process and also contains pocket of OH directly. So these are very effective, but of course, cement itself produce CO2. So that need to be some method you could reduce that production, or simply because you already have a lot of wasted cement we can use. So there are different ways you can do this and with different efficiency. So what ONCE program proposed is use this adding alkaline material to sewage treatment plant or to estuarine, because these are low pH environment that actually will not avoid a lot of pitfalls of other approach. And I'm not going to talk about how this could, how much to improve that, but I just want to point out in different stage, this is more natural currently going on. So initially, if you could have, with like 3 gigaton CO2 and or 3 petagram carbon, and then increase eventually to 10, 20. So I want to say a little bit about the advantages of adding alkaline material to sewage and coastal waters. First, it can avoid calcium carbonate precipitation, the secondary precipitation. If you spray the carbonate alkaline material to the open ocean, you will be sure to induce calcium carbon precipitation. But in coastal ocean, you probably can avoid that because of low pH in wastewater. Or even better, we can collect that at the sewage treatment plant. So that actually will lead to that process, that line, the last line, both decrease DIC and alkalinity. Second is minerals may be dissolved at a meaningful rate, like a silicated mineral, which is harder to dissolve in the open ocean. But in sewage, when you have these organic chelates and low pH, I think my time is approaching. And then, this should be CO2. So this reduce CO2 release and mitigate the ocean acidification effect because of the vast amount of sewage release. Basically what a sewage treatment plant is doing is it break down organic matter, release CO2. That actually is a CO2 release. So by fix that there, you don't need to do that much breaking down of organic matter. So to reduce CO2 release, and it could mitigate ocean acidification in coastal, in estuarine, right? And then you probably can remove pollutants on site much easier than after you spray like minerals to the open ocean and you had the trace metal release. But in the sewage plant, you could actually do this much easier. And economically, I feel this is a more viable approach than sending thousands of ships to the open ocean. So that's what I'm going to talk today, and so thank you again. Oh, go ahead.
We can take 1 or 2 questions, if anyone. Any questions? So if not, are you coming? Sure.
Hi, Wei Jun. It's Will from Planetary. It's good to see you. I really liked what you said about, well, I didn't quite understand it. They're removing the pollutants on site. Can you elaborate a little bit on why that's a key advantage to using wastewater pipes?
So you're talking about the removal pollutants on site, right?
Yes, number 4, I believe.
Like you have the trace metal may come out from like olivine, for example. So if you spray olivine to the open ocean, then it's very hard to remove that. So within the sewage treatment plant, you could install facility, equipment to remove that a lot easier.
Right, so you're saying you could add an additional step to make sure those trace metal additions are lower. I see. Okay, thank you.
Okay, thank you so much. Okay, so next speaker is Professor Zhou from Shanghai Jiao Tong University. It's myself. So I'm going to share with you about the collaborative platforms. So let me see. Okay, so few years ago, and we have been thinking about what kind of research platform we really need, which we didn't have in the past. So in last, say, 10 years, China probably produced about 20 research vessels at the world class. But with all these research vessels, what we really need? So, and we look at the chart on the screen. So basically we look at the spatial scale and the time scale. What we really miss is if you have extreme weather, say for example, a hurricane come, a typhoon come, most of the ships run away. You set a couple moorings, you never catch them. So we need a research vessel could sustain a large wind and stay inside, take a measurement of ASC interaction. And also we look at the carbon export process, which is not really at the average sea state. It's really event related. You have a nutrient injection and you have phytoplankton bloom and before zooplankton kick in and settled into deep water. But we miss that during regular vessels. So we are thinking about we need a large research vessel which can sustain for the extremely event and also can stay there over long time and take the measurements. So this is why we decide to make a ship, which is something happens not moving. Okay, so it's we call the International Mobile Ocean Observatory. So and the feature is it can sustain extreme weather and stay at the station for a long time, and also can move. And so we are now at the designing stage. It's fully funded for 3.8 billion RMB. So the design is the size is about 78,000 tonnage. And the dimension is about 140 meter times 90 meter. And the maximum speed of the mobile platform can move about 12 knots. And it can working at the sea state, 6 to 8. And if you have a hurricane, the wind class about 16, it can survive. So basically, if you have a regular hurricane come, you don't have to run away. So actually, it can stay over there. It can stay at the sea for 186 days, but we use resupply vessels, which means that platform can be on the sea for years, stay at one location or moving around nearby. And also on that large research vessels or ocean observatories, we have 6 labs which will be equipped with the world first class equipment. Then we have an ASC interaction lab and ecosystem dynamics and environment, and geophysics, trace metal clean laboratories, and deep sea life, and supercomputers. So basically, you can get onto that research in the observatory, basically start your work. You can have all kind of instruments, what do you need, probably more than what you need. So currently we are on the designing stage, so the construction will start from next year sometime. And it really have 3 goals. One is we take a measurement in the extreme sea, and also we look at the climate, basically from event to seasonal to interannual variabilities, and to look at the carbon barrier process. And also it has the deep drilling capacity. So in that way, we'll look at the deep sea and Earth explorations too. So it will be an international center. Basically, we will have a science steering committee, and we can have the collaborative projects. And also, if you want to run the laboratory, run the space, it's also doable. So it will be really an international mobile ocean observatories. So this is really something go along parallel to one's program and provide scientists the research capacities. The next thing is the marine environmental chamber system, like Nianzhi already mentioned about it. So the original design will be a very, very long chamber, which is about 8 meter in dimension and 50 meter tall. And it will simulate basically the ecosystem in oceans. The reason to have this is, in addition to ocean observatory, you do experiment on the ocean, but you really do not have a full control. But you have this chamber system, so everything you can really to control the experiment you want to do. So that's the idea. And this is still in the discussion stage, and the mini versions is already under construction, which is about 3.6 meter in diameter and 12.5 meter high. And so this is the kind of design over there. So hopefully it will be functional in next 1 or 2 years. So we'll build 3 of them. So that's the plan. So thank you very much. I will take questions.
Thank you for the nice presentation, and really exciting to see the plan of the ship. I was wondering if the ship also is exploring some sort of renewable or marine energies to essentially extend the length of, of the offshore life.
Yes, you can. So the ship is basically a platform with the imaginary capability, can do anything you want to. So, but yeah, you can do that.
I guess what I'm asking is, how is the ship going to be propelled? Have you
Oh,
thought
propelled, yeah. So, well, we mentioned we need a lot of the wind turbines and the solar panels, and also now it's also with the kind of diesel engines. So far, yeah.
Thank you.
So, are there any questions? If without any more questions, next speaker will be Chanan Zhang, who is going to talk about. So actually, I forgot your title, so I need.
Okay. Hopefully, I don't forget. All right.
Okay, here we go.
All right. Let's see. We have this is the laser pointer, and I can use this. Okay. All right. So I think we all remembered and we all liked the first presentation by Feng, right? So I'm going to learn a couple of her skills. First, step behind from the podium. Second, speak loudly. Okay, all right. So we have learned about what once is about, and today I am going to just to follow up on that, to be part of the once program, a project proposal under the Global Once to the UN Ocean Decade. I'm now located in Shenzhen, China. Okay, let's see. How do I go? It is the thing I should work with. Oh, okay. But that's, okay, the error. Come on, save me. I do not. Okay, all right. What is iCubes? It is the to integrate the ocean exploration science and technology to develop multi-functional application models in ocean climate change predictions. Shenzhen, if you have heard of this city, is very young, very dynamic. It's also very high-tech driven. And with Shenzhen is already planning what the monitoring system should be. First is high precision, real-time, regional synchronized, and multiple dimensional ecological environmental monitoring, just like this. The drone system, the satellite system, the land-based and water-based system are all being put together. And I think we call this the smart observation. And with this kind of system, we should be able to make some intelligent management to also benefit the society economically. All right. So I just want to show you one example, what kind of high technology we're developing in Shenzhen, the drone array technology. We're not just building one drone, we're building 10, 20 at the cost that are affordable. And this is one example how they would work. So I have 10 drones working together, lining up, or in circles, or in triangles. And these drones can be used on to hourly basis. We can do sampling 2 hours, 4 hours in a particular location, and they have sensors attached to them. And this is just what we did in the triangle place, a 3 zone to work with to collect data. And because of this zone system is very flexible, amongst big ship can flow on the surface of the ocean for 120 days and get recharged somehow. But for these zones, they are mostly used now in coastal regions because we know one particular problem, that is the OMZ. So we are designing the system. We can do the carbon flux measurement, and we can sample in the area that spatially and temporally coordinated. Okay, so a colleague of mine, Helmut Thomas, who will be in our discussion session, he said what we can do now, and we can do it safely, is to do better on monitoring, on recording, and on verification. And I think we can take out things from the water more safely than putting things into the water. So with this system, I think we can achieve this goal. So to the left, we have a visualization of all the parameters to be displayed. In the middle of the panel is the actual environment. We can click on that and to see what kind of parameters would display. Dissolved oxygen, salinity, chlorophyll. Right now, the integration of the zone system and the sensor system can work together for up to 12 sensors. And to the right panel, we're still developing so we can have monitoring as well as prediction or warning system. And we also do microbiology at very large scale. I was trained as a geologist, but I learned my way into microbiology, and I think the unseen majority need to be visualized as well. So to the right, we have sampling at 16, 20 T size data, and we want to realize that in terms of the daily rhymes of the microbial property, because as the skill gets into detail, I think we can find better, we have a good understanding what the underlying mechanism would be. So I think with that, I just to show you, we have a good team integrating technology, engineering, physical oceanography, chemical oceanography, microbiology, and we can really expand this team to seek collaborations at this meeting. So yesterday, Brad and Dave from the Ocean Visions, we sat together, we talked about collaborations in the future, so I hope really that's our next step to be realized. Okay, I think with that, I'll stop here. Thank you. It didn't work.
We can take a couple of questions.
Hi there. I was just hoping to hear more about how you're actually measuring the CO2 fluxes from the drone.
Right. Okay, that's a great question. You see, in that design, we have a PCO2 measurement in the air and also a PCO2 measurement in the water. And we hope to measure both simultaneously. And my colleague, Wei-Jing Kai, he's the expert on the carbon fluxes, but we are trying to develop this, these two measurements simultaneously. And I asked Wen-Jun, it is going to be meaningful because traditionally we do CO2 measurements on a boat or something, not simultaneously at all. So I hope this will provide a better precision for that kind of measurement. We're right now in the testing of that measurements.
Thank you.
Sure.
Okay, we need to move on, and thank you very much. We cannot succeed to deal with climate change without the tremendous support from international collaborations. So it is my pleasure to introduce you Professor Fei Chen from the University of Maryland Center for Environmental Science. Okay, please.
Hello. So my talk today is about the enriched oxygenase gene in the deep ocean. Let's see. So I guess most of you knows about carbon cycling in the ocean. So we know that there's a large organic pools, dissolved organic pools in the ocean, and refractory DOM pool makes up about 95–97% of total DOM in the ocean. So this recalcitrant or refractory DOM is very important because they can stay in the ocean for a long time. It's considered as a carbon storage capability there. And then microbial carbon pump was proposed in 13 years ago by Nianzhi about to emphasize the microbial process, the importance of microbial process for the formation of the refractory DOM. And however, most of the microbial metabolisms and biochemistry details still remain unknown. So my talk is about oxygenase, and I just want to show you that the oxygenase can be divided as monooxygenase and dioxygenase. So there are also other oxidative enzymes out there like oxidase, and they are different from the oxygenase. As you can see from the name, the monooxygenase actually add single oxygen atoms to the substrate. Dioxygenase add 2 oxygens to the substrate. And these oxygenases can further carry on the degradation of these organic compounds. A lot of them are aromatic, polyaromatic, or cyclic compounds. And oxidase, I just want to point out that, a lot of people confuse oxidase with oxygenase sometimes. Oxidase does not add oxygen to the substrate. It uses oxygen as an electron receptor. And the substrate they add on is slightly different from the oxygenase. So they work on a lot of chain compounds, a short chain. So this is all I know about the organic chemistry here. So what led to my work, or the logic behind my talk here, is these key points. We know that DOM is the largest reduced carbon pool in the ocean. And oxidation of DOM is probably the most important microbial process in the ocean that affect biogeochemical cycling. And oxygenases are abundant in nature and commonly add on cyclic DOM and make them more degradable. And most recently, a large numbers of oxygenase gene has been found in SAR-202 bacteria, which thrive in the deep ocean. So my work is really inspired by this paper published in 2017. Basically, they analyzed the metagenomes of SAR-202 and found out there's a lot of oxygenase gene and monooxygenase gene carried by this group of bacteria. And so to me, this is pretty amazing, where you see a lot of oxygenase present in this very abundant microbial group that is very abundant in the deep ocean. And this group has not been cultivated and has no cell wall. I don't know, how they grow in the deep ocean, but it's a kind of mystery right now. But just to show you how abundant this SAR202 is, and you can see here. So this is the vertical profile. You can see SAR202 can make up about 10, 20, 30, 40% of total bacteria counts. So SAR202 are very important bacteria in the deep ocean. This number is based on the total phytoplankton counts, so a little bit lower, but you can see the trend is about the same. So my question is, are oxygenase genes present in different bacteria groups and different depths in the ocean? So we conduct the metagenomic studies at the BAT station. We took samples from 6 different depths. As you can see here, this is the depths, 6 different samples. 2 of them are in the euphoric zone, 1 of them from oxygen minimum zone, and 3 of them from the deeper samples. And we perform metagenomic analysis. That's the flow chart here. And because we use ultra deep sequencing methods, and it allows us to get more assembled genomes. And here, as you can see, we compare to Tara Ocean and Malaspina genome sequencing. Our sequencing depth is much higher than Tara Ocean and Malaspina samples. And this allows us to get much more MAGs, metagenomic assembled genomes. So we recover a total of 60,000, more than 60,000 non-redundant oxygenase genes from these 6 samples. And you can see here how these oxygenase genes are distributed in different taxa and different depths. And 2 things I want to point out here is, you can see from the surface water in the euphoric zone, oxygenase genes are much lower compared to the deeper samples. And chloroflaxi is here, and you can see that SAR202 is right here. That also means that other bacteria also carry a lot of oxygenase genes, not just SAR202. So when you get deeper, you get more oxygenase genes. And if you look at the oxidase gene, which doesn't add on a lot of these cyclic compounds, you don't see this kind of trend. All right, so you can see from the surface to the deeper samples, you don't see this increase of oxidase genes. And we can further break it down to we can further break down oxygenase gene into monooxygenase and dioxygenase genes, and they make it about equal amount, so they about half-half. So this is the monooxygenase and this is dioxygenase. And we can break it down based on their cofactors. And you can see here, we have a flavin dependent, and we have iron dependent, and we have also iron dependent dioxygenase, monooxygenase, and other. The 2 dominant one are flavin dependent monooxygenase, this one here, and the iron dependent dioxygenase. These 2 are the major form of dioxygenase in the ocean. And again, you can see that the numbers increase a lot when you go deeper. We can also break it down based on their the compounds, the substrates type. So we divide them into 6 different families. This oxygenase, like this one, family 1 is for aromatic ring degradation, and family 2 is polyaromatic ring degradation, and family 3 is for sterol degradation and other ring degradation. As you can see, that this very complex organic matters here, from single ring, double ring, and multiple rings. And the genes are here, and you can see that the number of the genes increase significantly when you go deeper. But this is not the case for the family 5, which is a short chain molecules. It's not ring structures, and you can see they are not abundant in the ocean. So this just tells you that the oxygenase gene play an important role in the deeper ocean. So that's the kind of recapture of what I just show you. I think the take-home message is that when you see a lot of organic, oxygenase gene in the deeper ocean, and microorganisms probably adapt to this environments, and they can add on a lot of organic matters, which can be more recalcitrant or semi-recalcitrant or semi-recalcitrant, those semi-labeled DOM. And I want to thank Tom Fei, who is the key players of this metagenomic analysis, and many of colleagues that help collecting samples. Michael Gansier, who is also here, is the PI on this project, funded by National Science Foundation. Thank you.
We can take one quick question. If without any further questions, so thank you so much. Okay, thanks. Okay, so the next speaker is Dr. Marcus Wimbois from the Laboratoire Oceanography de Villefranche, but he cannot make his way to here, so we'll move on to the next. So next is Professor Michael Gansier and from the University of Maryland Center for Environmental Science to share their work, the marine dissolved organic matter reactivity continuum concepts. Great, thank you. If you can take it off, we can leave it here. So the next is, okay, here we go. Oops.
All right, thank you. My talk is a little bit about what we know and what we don't know, because I think we should keep in focus how important it is that the fundamental basics are there when you even talk about carbon sequestration in the deep ocean. And we recently introduced a more, I think, comprehensive way to look at the reactivity of organic matter in general in the ocean. It's essentially an adaptation from the freshwater world and the sediment world as well. So it's really not the novel concept, but we have compartmentalized marine DOM in just simple categories like label, semi-label, and what we call refractory dissolved organic matter. And I'll show you a little bit of data, so what we need to think about and maybe revising even what we do know as, or what's an accepted view right now. So let's review a few things. People working with DOC or dissolved organic carbon knows this quite well. Dennis Hansel's work, groundbreaking work, that we do know how much dissolved organic carbon is in the oceans. So we know there's about 80 micromolar per liter carbon in the surface and about 40 plus minus, a little bit more in the Atlantic, a little less in the Pacific. So we already heard that number about an inventory of 662 gigatons. So that's quite a large pool. Just put in comparison, is almost as much as we have carbon dioxide in the atmosphere in terms of carbon. Theoretical exercise here, just 1% additional mineralization of that pool would entirely offset the entire anthropogenic production of CO2 on an annual basis. Just to put into perspective how much carbon there is and how little we understand this in terms of its dynamic and reactivity. We do know, though, that it's largely controlled, that the DOC we're measuring in the water is largely controlled by nutrient availability and primary production. So that's pretty established work. Here again, a bit of review what we have. Surface ocean on the top, about this 80 micromolar. Of course, we have regions where it's a lot less, but then you see also at the bottom part, there is quite a lot less in the Pacific than in the Atlantic. There's still a lot of controversy why that is. There's some interesting ideas about how carbon is utilized on long-term transitioning from the Atlantic to the Pacific as one example. Here's the prediction. That was a nice paper basically looking at modeling DOC calculated based on nitrate. And it's a pretty good prediction. So basically what this means that you can directly predict DOC in the surface ocean from nitrate availability, meaning primary production. So I think that puts really a good key information out there that the DOC we have in the oceans are mostly produced by primary production. Sure, there's supplies from rivers and so forth, but it's extremely minor if you take this one. So that's just the key of photoautotrophs. So DOC comes carbon, we're fixing carbon, right? So algae fix carbon and then consequently will produce DOC. But I want to also go to one more thing here, and that's the deep ocean primary production. We ignored for longest time. So the chemoautotrophs or chemolithotrophs. So newer data shows actually that they're very important. So one estimate is about 1 petagram carbon. So that's quite a lot of carbon per year being fixed by marine nitrite oxidizing bacteria, nitrospinase. So, but they need to have nitrite in the first place. So what about the production of nitrite by ammonium oxidizing bacteria and archaea? So far, we have no idea how much DOC is coming from the primary production in the deep ocean. Keep that in mind, completely ignored with budgets right now. It hasn't been calculated. We base our assumption about how carbon gets in the deep ocean out of a two-end member mixing model coming from the surface through the biological pump and microbial carbon pump processes. Here's my own data. This is just looking some fluorescence profiles, and that's the correlation between Atlantic and Pacific station, Bermuda Atlantic Time Series station Aloha and Hawaii. There's a lot more of this fluorescent material in the Pacific here than in the Atlantic, but yet the opposite trend is true for when we look at dissolved organic phosphorus and dissolved organic sulfur based on solid phase extracted material. So why do I show this? This shows the fundamental differences in the composition of that organic matter, even though concentration are not that far different, even though we have a little less carbon at the deep ocean and Pacific than Atlantic. If you look at this, this is combined data, historic data, a lot of data behind this actually from the historic sampling at those two stations. You see that the Pacific has quite a lot more surface DOC, but a lot less DOC at that depth. So that means there's higher primary production at the surface. You can all probably agree with me now when I showed you the slide about that carbon fixation is the source of DOC. But why is there a lot less? So the old hypothesis is there's a slow degradation through meridional overturning circulations. But I think it can be easier explained by surface to depth processes, and that just in general how larger percentage of the DOC in the Pacific is essentially more labor and can be utilized quicker. Here's an old data from 1992, which got us thinking that the deep ocean DOC is really old. About 6,000 years in the Pacific and 4,500 years in the Atlantic. I want to caution about this. This is a C14, apparent C14 age, but any DOC coming into the system, which is older than 50,000 years, is C14 free and will bias that view. So that's a two-end member mixing model as well. So we do now know there is actually C14 sources for DOC in the deep ocean from seeps. We have oil seeps, we have hydrothermal vents, we have methane seeps, we have ancient CO2 seeps. We don't know the exact number by this, but we do know that it influences this, and the C14 community is actually working on this right now, but the marine biogeochemists are still talking about thousands of years old DOC, which is probably not quite accurate. In fact, I would argue we don't have any clue how old this actually refractory DOC really is, despite the C14 data, which I think could be quite dramatically biased. So I think if you do the calculations and you just infer a little bit more of a degradation potential in the Pacific, then a similar amount of C14-free depleted DOC in the pool in the deep ocean could explain both ocean basins' age. So here's Dennis Hansen's estimate for turnover of a global export rate of 1.8 petagrams per year. So I want to just give this number, then if you could ignore C14, that's 370 years. That's a lot younger than thousands of years. So, and that completely still ignores the dissolution of particulate organic matter and the chemoautotrophic production. So we have here are the sources already mentioned of additional C14-free material. That way, I think we cannot just use the parent foot in CH to be the age of DOC. We have to look at autotrophy in the deep ocean. We have to consider C14-free sources, and we have to look. You have to reevaluate the turnover of deep ocean carbon. So I'm running a little bit out of time, so I want to get to a little bit of the model. I don't think we need to consider that DOC to be very old, but we don't know how old it is. That's my point right now. We need to get tools to actually predict it. But it's really important that we do, because that really is the key information we need to think even about to sequester carbon in the deep ocean. We need to know, we need to essentially develop traces for reactivity pool, and this is a pledge to my fellow chemists to really look into finding structures in the deep ocean DOM and really try to look into the refractor DOC pool to really get at a better prediction of how fast this material can turn over under extreme conditions like pressure and really low temperatures. But without knowing any of the structures, we can't even predict it, even with predictive tool in terms of chemistry. Here's the concept. We think we have to look in a more holistic way about the degradation kinetics. So the reactivity should be really not divided into large brackets, but more modeled in a continuum realm. So we put a perspective paper out. If you're interested, please read it. There are modelers who also think along those same lines, but we have no idea at the moment how old this DOC is in the deep ocean. And I think I just want to, one word of caution is, I don't believe that we can sequester carbon for thousands of years. That's my point. So I hope this is fruit for discussions, and I'm happy to take any criticism, of course, as well. Thank you.
Okay, we are going to skip the question, and because he will be on the stage, so next is discussion session, so we can have questions later on. So thank you all for your wonderful talks, and now you see WUNS is such an ambitious international program, and the question is how we can move global WUNS forward and to make it more international, enlarge its capacity, and empower scientists and engineers. So next section will be a discussion section and led by Professor Chuanren Zhang. Okay, please.
All right. Okay, it's me again. The rule is the rule, and we'll have to finish this session by 11:05, maybe a couple of more minutes beyond that. So I would like to call our panel members who are here to be on stage. And I will just do a brief introduction. So you want to come up, Michael? Okay, so it is my pleasure to have a brief introduction of the panel members for the following discussion theme. First, let me introduce the three panelists who are online. Nianzhi Jiao just showed his face a little.
Hello, can you hear me?
Okay, hi Nianzhi. Professor Nianzhi Jiao is from Xiamen University, China, who developed the microbial carbon pump theory and is the director of the Global WUNS program. Hello, Nianzhi again. Professor Dennis Hensel is from University of Miami, Florida, whose expertise is in marine organic biogeochemistry. He is the chairman-elect of UNOS, in charge of a big fleet of U.S. research vessels. Professor Helmut Thomas is from University of Oldenburg, Germany, whose expertise is in chemical processes in the ocean. He is the director of the Helmholtz Center, Harian's Institute of Carbon Cycles. Okay, and now the panelists sitting on stage. I guess I will just do alphabetic ordering of their first names. Dr. David Keller, good to see you. All right, from Gilmer, House Center for Ocean Research in Kiel. I visited there a few years ago. All right, good to see you. Dr. Lata Gawadi from University of Goa, India. Good to see you here. Dr. Michael Conathan. Finally, we met. All right, good. From the Aspens Energy and Environment in Washington, D.C., right? Okay. And Dr. Michael Kansier, who just gave a wonderful presentation. He's from University of Maryland. And finally, lawyer, Dr. Romney Webb from Columbia Law School. Let's welcome everybody. Give them a hand. Okay. All right. Thank you so much for staying with us. I think first we'll ask Dr. Nianzhi Jiao to give us a very brief expansion on the most feasible approaches to use engineering or CDR in the WANS activities. I think, Nianzhi, we need to hear from you. How can the WANS program be creative?
Okay, so can you hear me now?
Yes.
Yes? Okay, great, thank you. So, well, it's hard to see which is the best, but to the best of my understanding, appropriate approach for WAN should be theoretically reasonable and practically feasible and ethically legal. So that's the three principles to my understanding. So therefore, I would like to see with culture-based comprehensive WANS approach would be a kind of paradigm, because you can use clean energy to drive the artificial upwelling to burn up the deep water with high nutrients to support the carbon fixation by the seaweeds as well as the phytoplankton in the aquatic zone. And meanwhile, the upwelling can release the bomb of eutrophication in the bottom of the sea and mitigate the hypoxia and water acidification down there. Furthermore, you can apply alkaline minerals to enhance the alkalinity, and then you could turn, and as I said, the carbonate counterpump to be a positive one. And meanwhile, you can promote the BCP, I mean the biological carbon pump, as well as the microbial carbon pump together to achieve maximum outputs of carbon sequestration in the ocean. So finally, it is in accordance with the landing protocol. So I think serving the culture-based comprehensive way is reasonable, feasible, and legal.
Okay.
Charlene?
All right. Thank you so much, Nianzhi, because we really, I hope we have the speed and enthusiasm of the first speaker. So we have to speed up, really. I think we'll go to David, Dr. David Keller, to briefly tell us any possible synergies between WANS and the ocean nets.
Okay.
Yeah.
Thank
go
you.
ahead.
So Ocean Nets has been going on for several years right now, and I think some synergies are, well, we've done some fundamental work that can certainly be built upon in WANS, and we can also provide some lessons that we've learned from working together as an international consortium. And I think this will be valuable, that we can hopefully pass on what we've learned, as well as make, well, all our data and results will be available for you to build on as everything continues.
All right, great. All right, so next I'm going to ask my old friend, Dennis. Thank you so much, Dennis, for really coming online with us. Sorry you couldn't be here because of your back pain. I learned how that can be painful. But thank you for being here with us online. So the question is whether you can tell us how the international community organized in the past to make important advances in topics related to uncertainties in marine CDR.
Yes, thank you, everybody. Let me thank the organizers of the meeting. I've learned a lot from this meeting so far, and the session's been really wonderful as well. That's a good question. We need to, learn from what we've done in the past, and so for myself, I was struck by Matt Long's comment the other day that 6 months ago or so, he realized suddenly this marine CDR was rising quickly as far as an activity and interest. And I'm one of those people. I didn't know, I wasn't paying attention to marine CDR because I've worked in the fundamental carbon cycle of the ocean for going on 40 years basically, and that's where my head was. So I lifted my head and found out this was going on. I suspect it was the IPCC report that has made us all aware of this. So my coming here, was a learning opportunity, see what's going on. And I see now that there's a lot of great science going on in the marine CDR space. And no worries there. We heard in this session about it. We've heard it in the past sessions and, with the startups and with the scientists and all that sort of thing. And there will be more science going on with the verification side of the equation. No question about that. I recently looked at Lisa Levin's paper from March in, I think it was Science Magazine, and it was about the impacts of marine CDR. And that's, something I would like to see the ocean science community more broadly be thinking about. What's the impact science that we need to do? And that's where the opportunity for international coordination remains. When I got into this business, I remember taking biological oceanography class, and it was all about phytoplankton supporting fisheries. And then there was a big inflection point, and phytoplankton were supporting export of carbon. Carbon became a big deal. So we may be another inflection point. That was on the order of 40 years ago. That's when John Martin wrote his paper about particle flux using traps and all that sort of thing. And so I think it's important that we figure out the impact side, and we have to be sure, to protect the assets that we have in the water now. The observing systems such as the Ghost Ship, the Long Line program, observing program, the time series programs, the global biogeochemical Argo float system. That is funded for now, but I think there's no funding guaranteed after about 5 years, and so that's a big issue. And the bigger question then for me is, what are the sensors that we need for that?
Okay, thank you so much, Dennis. Sorry, I have to cut you short.
Yep.
Because I want to come back to the stage because we need to have a gender balance. And I think we'll start with Lada. Yeah, go ahead. My question, yes. Well, you are as enthusiastic as fun. I use fun a lot. As a good model. You participate in the global ones very enthusiastically. What is your suggestion on how to bring about climate change knowledge exchange between scientists, community, and decision makers?
Thank you, Professor. I think it should start at the grassroots level, like starting what I do usually in my country, like focusing on the young minds, like school children, then the higher education institutes, then going to the community, and when this happens, finally going to like policymakers and the political leaders, so that makes the path easier. So that becomes like a regional level exchange of knowledge and awareness, and then going to national and international level, the kind of ones that we are doing right now. And I think these are the community or the young minds. These are the main actors and factors that can contribute significantly to exchange of knowledge and awareness, and finally contributing to the climate change impacts.
Okay, yeah. Great. Thanks, Lada. I think I do not want to lose our lawyer here, so I'll go with Romney Webb. Your expertise is in legal issues associated with the development and deployment of negative emission technologies. What opportunities do you see collaboration on ocean CDR governance?
Yeah, thanks for the question. I think that, we've heard a lot over the last few days about the sort of science and engineering challenges in this space and the need for more work in that space, which is absolutely true and very much needed. But there's also a lot of really complex and challenging legal and governance considerations in this space that require attention as well. And I think there's a perfect place for greater international cooperation. You can see a lot of benefits from promoting learnings across countries around how to effectively govern activities in the ocean. When we think about ocean governance, we tend to focus on sort of international governance frameworks, which exist and are important, but there's also a lot of domestic law at play here, and there are, I think, real opportunities for legal researchers in this space and also for decision makers and governments to learn from each other's experiences and to take, to figure out what works and what lessons there might be from other countries. So.
All right, thank you so much, Romney. I think I will use the final 2 minutes to ask Helmut online to use it. Helmut, we have published recently, but this is the first time we actually to meet each other online, so it's good to see you.
Yeah, thank you.
Right, my question is, how do we best use monitoring, reporting, and verification in maintaining ecosystem health under the global climate change pressure?
Yeah, let me briefly thank the organizers to invite me and also to set up this brilliant session. I think what I see for Global Ones is really a task to unify or to agree upon a set of monitoring, reporting, and verification measures which can be applied globally and will be accepted globally. And this also connects a little bit to what the preceding speaker said, that in the end, our efforts in negative CO2 emissions would lead to nationally determined contributions according to the Paris Agreement, that the countries can show that we have done actually something. And I think for this, we really need good and all over the earth accept or planet accepted tools, because I think in particular in the ecosystems, of course, we can think we would draw down CO2 from the atmosphere, but in the end, we need to know whether the whole ecosystem actually then behaves as a thing, or whether it's not only one flux we change. And I think Global Ones can play a pivotal role here in establishing such tools and measures and agreed upon protocols.
Okay, all right, thank you so much, Helmut. So, Mr. Chair, do you think we can just finish here? Okay, and to Michaels, I'm so sorry. We have to go for a beer to, ask to learn about your questions. Okay, all right. So, guys, thank you all very much. Let's give them another round of, Thank you.
Caroline.
Yeah.
So we're finished?
Yeah, I think we're going to finish. The chair asked us to really finish up here. So you want to say one thank you, 2 words?
Yeah, of course. As the co-chair of the Global Ones program, I would like to take this opportunity to give my sincere thanks to all of you for your attending the event session, particularly to my co-chair, Professor Carl Robinson, and the panelists here, and my colleagues, you. You attended the meeting in person, and your presence and contributions are invaluable. And my apologies for unfortunately not being able to make it to Atlanta on-site in person to be together with you. But I listened to all the talks in the session, and all are wonderful. The talks are from different discipline and from different angles, but toward the same goal, to make the ocean negative carbon emission to be reasonable in theory, to be feasible in practice, and to be legal in ethical regards. So now I can see we have made a great step toward this goal today. And I hope you can, all of the attendees, find these special events to be informative and to be useful. I would like to encourage all of the meeting attendees today to reach out to Ones, to ours for any further questions and information for collaborations in the future. And then I'm always to be happy to together with you for discussions, for shared facilities we have, and for collaborations with you. Okay, so once again, thank you very much for attending the one session, and thank you all dear speakers, dear panelists, very much. Goodbye.
Goodbye.
All right. Thank you. Sorry, to have to cut this just a little bit short of what you expected, but we are behind time. We have a short break here, so please gather a little bit of refreshment, and then we're going to have our final 2 sessions before we close out the conference. So thank you all very much. Thanks to the Once program for coming in such force with so many people and provocative ideas. There's going to be a lot of follow-up, I'm sure.